Hey everybody, oh, that's pretty loud. Hey everybody, my name is Aaron Buchwald. Just that a little bit. Hey everybody, yeah. Hey everybody, my name is Aaron Buchwald. I'm a software engineer at Avalanche, or as I've always wanted the opportunity to tell this joke, Buchwald Incorporated, the leading provider of Buchwald services. Today I'm going to be talking to you guys about benchmarking blockchain performance. So this won't be as much about the workloads that we're using or how to benchmark blockchain performance itself. I'm going to try and go into what the incentives are that people are actually following when they produce benchmarks they talk about on Twitter, and how this leads to some effects that we actually don't want, and make what I think is an interesting prediction for what the next era of blockchain performance will look like. So why are we benchmarking? The traditional answer, or the reality of the answer, has been tweets, VC pitch decks, tech is good, and tech is improving. And this is a price chart that I grabbed from CoinMarket, or actually ChatGPT generated this for me. I couldn't find quite the right price chart to look for, but this is if you actually look at the benchmarks people are posting about their TPS numbers, etc., I think that this is the actual motivation of most of the numbers that you see on Twitter. But there is actually a completely separate motivation that underlies what we're trying to get at, and it's much more specific than this. And so why are we actually benchmarking from a real system design perspective? Well, we want to pursue continuous improvement and optimization. We want to determine what is the actual safe target utilization to set. Going back to Steven's talk about fees, in order to actually set that target utilization that determines what we want to run at in order to set fees around that basis, we also need to know what a target utilization is that we can run at for the long term in order to say that we're going to be able to run at this and have predictable performance around that number. So we really want to guarantee that if we set the target to 8 million, 10 million, 100 million, or a billion gas per second, then we want to make sure that when we do it, we can have predictable performance. We want a system that runs forever. And then I kept tweets in here from the previous slide because I do think that's important, or maybe not important. I do think this is somewhat of a reality of you want actually both the ensuring predictable performance, and you also want the number to tweet about to some extent, so I kept that. So the focus of this talk is going to be how do we go about determining that safe target utilization, how to cheat, or what you actually see oftentimes, or make sure that you don't cheat yourself by mistake, and as I said, one bold prediction for what the next era of blockchain performance will look like. So what we'd like to do in terms of setting the target utilization is pursue data-driven scaling. It's very easy to pursue YOLO scaling, to sort of say, we're going to keep increasing the gas target forever and have no data that underpins that. You can do this in a conservative way where you're increasing the gas and are able to pull it back if it actually doesn't quite, your system doesn't quite scale up to that point. But what we'd like to do even better is say we actually have the data from testing our system that we can run at any given point in time and say we're comfortable running the system at this level of performance. And this way, when we come up with optimizations like streaming asynchronous execution, Firewood, or any other optimizations, we're able to put them into the system, the performance lab, and say, after making this optimization, we're able to 2x the gas limit. Right? And so with something like streaming asynchronous execution, the estimate that I think we've had is because of the way it enables us to optimize how we're spending our time, we should be able to at least 2x the gas target, ignoring some of the other factors we want to account for. And with something like Firewood, we should be able to 2x it again. And so in order to pursue actual data-driven scaling, we need to have some system where we can plug these things in and say, this is what tells us we're actually able to safely increase the gas target. So a few of the factors we very, very specifically want to look at is we want to look at our worst case performance. In order to have predictable performance in a system that is Byzantine and permissionless, we need to think about what is the worst possible thing that can happen. So a Byzantine user can, as Steven pointed out, at any point send a transaction that triggers our worst case. And this means that if there is anything in your system, whether it's writing random writes to state, a particular precompile that's inefficient, if this is the slowest thing, a user can trigger it at any point in time. And this is our worst case. So we want to make sure that if we are allocating 1 second of total execution time, we are pricing that correctly so that as we increase the limits of the system, we're making sure that we're never going to have price 1 second of computation or utilization, and it's actually going to take us 2 seconds to perform. If we have something like this, then we end up in a world where the system can start to fall behind. So we'd like to have a tight bound on what the worst case block verification latency is. And we'd also like to have purpose-built chains that are able to benchmark for their specific application. That are able to say, because we're doing something even more specific, let's say there's two things, A and B, and A can be done very efficiently, but B can't. In a totally general purpose system, if we want to benchmark for our worst case performance, we need to set those limits based off of B. If we're in a highly specific system where, let's say, we can place a tight bound on the size of the state and can keep the entirety of it in memory, we might be able to set a much more aggressive limit and still do this very safely and still do this in a way where we have a very strong understanding of how our system is going to perform. And the last piece that I wanted to add is we also want to understand how our system is going to perform a year from today. So the worst case block verification latency today is a function of how large the state is, what are the available opcodes and precompiles that can be paid for by anybody in the system, and how much you can cram into a single block. But our state is dynamic and always changing, as well as we ship new changes, as we change the consensus engine, et cetera. What we can actually do changes over time, both because of factors like state growth, write amplification, et cetera. And this means that we also care about what do we think is our worst case going to be a year from today. And we worry about that today because whatever we price today, however much gas we allow to be consumed, determines how much state growth can happen in the worst case and also is likely to happen over the course of the next year. So one factor that we really want to consider and that app chains and purpose-built chains should consider as well is not just your worst case verification latency today, but what do you think your worst case verification latency is going to be a year from today? After that, we can sort of consider worrying about this less because, one, you're able to dial back the limits if you see fit, which maybe you won't be able to sustain the same performance if you end up in that boat, or you might be able to come up with optimizations in that time. And if we want to compete for distribution and market share today, then we can take an aggressive approach, but want to do it in a data-driven way. So a safe target utilization ought to be determined by these factors. As I said, blockchains are typically public and permissionless, and users can easily pay to trigger your worst case. So, we need to have a system that has some target utilization so that it can shed load when it's overwhelmed or above that target utilization. There's typically two ways that we do this, or two ways that you could do this. What Solana does is they'll actually throw away transactions and not necessarily increase fees or have some of their local fee market that will determine which transactions get included. But you can have this sort of first in, first out system, which under load, if you're not prioritizing based on fees or any type of auction market, then some transactions will get thrown away and they don't necessarily have a way to express that they're willing to pay a higher price to be included. The alternative to this is EIP 1559 or ACP 176 style mechanisms, where you can actually say, here's how you express your view that I want to pay as much money as is necessary in order to be included on chain. And so you can say, if the chain is under load, I'm willing to pay more money than the next person in order to be included. And this is typically a better load shedding mechanism. Markets are a great mechanism, and in blockchains, we typically take things that have inefficient markets and try and apply markets to them. And so we might as well do that with how we include transactions on chain, and this is generally the most effective way. So, this is the graph that I stole from Steven, although he stole it from the Snowchase Explorer, which shows that's exactly what we got with ACP 176, is we used to have this system where it was not accurately targeting our target utilization, so we have a system that's much harder to predict. And after ACP 176, we actually much more clearly, you can see here, target our actual target utilization, and so this number is much more meaningful to us now. And so when we talk about raising that limit, we have a very clear idea it's actually going to change the utilization there. Now we still have further factors to consider here, like how much of that is allocated towards state growth or state allocations, which is going to play a big role in what is our worst case verification latency going to be in 1 year. But overall with ACP 176, we have a much better idea of what our performance will be like in a year and what our performance will be like at any given point in time. So what do we actually want to benchmark? Well, first of all, we want to benchmark, as I said, the worst case. We want to know and understand what is the worst thing that can happen on our system, both for a general and permissionless system, as well as for purpose-built chains doing something a little bit different. So we want to understand this so that we can guarantee predictable performance. We also care about average case to a certain degree. We care about average case in particular when it comes to how much state growth is actually happening in our system, because this is a fairly good guiding factor for, are we actually in a system where 100% of our capacity is allocated towards our worst case, or our worst case for state growth, Or is it going to be, let's say, 20% of gas will be consumed towards state allocations, which means that we can actually set our limits to be a little bit more aggressive? Or do we even have something like multi-dimensional fees at some point in the future that enables us to have even tighter bounds on what that performance will be like in a year? So this is what we want to understand is what is that worst case block execution time, and given we want to have those tight bounds on worst case execution latency, what do we need to do? And so this enables us to understand that. We want to have a system set up so we know how any individual optimization will impact it. And at the same time, we want to use this data in order to inform a data-driven scaling approach. We want to scale aggressively, but with that data-driven approach. So with that, what resources are we actually utilizing in the EVM and in blockchains in general? Well, it's very simple. We are typically utilizing CPU, bandwidth, and then state access, which can be broken down into read, write, and allocations. So I'll go into each of these resources and then also talk a bit about both what the class of optimizations are that are relevant to them, and then also how you might cheat with those benchmarks, or how you might come up with a benchmark or a case workload that performs better, even if it may not be relevant to your production workload. So I'll go into a little bit of these details. So the first one is CPU. How fast can you run your system, right? So you can look at the benchmarks for EVM precompiles and see that for some of them, they're typically operating between 50 to 200 megagas per second. And if we want to scale up beyond that, typically the strategy we want to do whenever possible is to scale horizontally. And so we can do this with parallel execution. We can scale up the number of cores fairly arbitrarily, and this has been how we scale systems over time over the past 50, 60 years. Once you do that, however, you do have to choose between pessimistic versus optimistic concurrency control, and these have their own trade-offs as well. In order to give you an idea of what is the maximum performance that you're going to get, don't trust these numbers too much, but a ballpark number of an EVM transfer in a very, very simple Golang benchmark, which doesn't have the same garbage collection, memory overload, or even anything related to the Merkle DB, or, in order to come up with a more accurate number. But as a ballpark to inform it, if you look at a benchmark of EVM transfers, it takes about 30 micros. So if the only thing that you had to do in the system was just the CPU execution of creating the EVM interpreter and then executing a simple transfer, the max that you could get per core is about 30K transactions per second per core. In order to go beyond that, you would probably have to scale up to further cores and figure out how to break down parallelism and figure out how to price it as well. So what are the gotchas with this system? The first one is going to be handling conflicts. So it would be great if blockchains could scale to the entire world's resources, or everything that we could want to put on chain, and there were a good breakdown of people are accessing different states at different points in time. But the reality is blockchain workloads today don't look like that at all. And this misconception, or this separation between reality and what we would like in order for these idealized workloads to actually happen, is where all of the mismatch comes from. So as an example, Stephen pointed out, I think it was the MapleStory release happened last week, and at that point in time, there was probably very, very little opportunity for parallelization because everybody was accessing effectively the same smart contracts. So although you might look at it and say, well, if we're operating above capacity, we should throw more cores at the problem and we'll be able to compute more. This actually doesn't work if you're accessing the same state, because you need to have some way in order to linearize the execution, in order to say this transaction happened after the other one, and make sure that they have a consistent view of the state. I included Trump as an example here. This is something you guys are probably all relatively familiar with, is that oftentimes blockchain execution is much more so everybody's doing the same thing at the same time. If everybody were doing something a little bit different, accessing different data, we could parallelize much more effectively, but unfortunately that's not quite the reality. Additionally, you do have to require some type of fee market in order to limit worst case cost of parallel execution, and this is a relatively unsolved problem with no exact system that works perfectly and is not subject to some degree of messing around. Another alternative from database systems is snapshot isolation, and this means that, I got a little louder. Can you make that a little quieter? What's that? Okay. This means that after you, when you try to access the database, when you try and perform a read and write, each transaction will get some initial view of the state, and if that has changed by the time it tries to commit, you'll just throw it away. This means that you don't have the guarantee you want from blockchain execution, where although you'll never have a transaction that tries to read the state, and then ends up performing a write that doesn't match up with what's read set, it does also mean that you're going to be paying for on-chain execution and then throwing it away at the end. So there's some degree of wasted resources here. And it's probably not the DevX that we want for blockchains. So we do have this hard trade-off of how are we actually going to parallelize transactions when they all want to touch the same state. And this typically devolves back into anything touching the same state needs to be executed sequentially. So the next gotcha is bandwidth and enhanced block propagation. This is the term that I found. There was a meetup in New York City recently that I really like, which is just enhanced block propagation. I think this really accurately describes what several people are building in slightly different ways, all targeting the exact same problem. And this is that at a certain layer, when you're scaling up the block size or the amount of bandwidth needed by the system, the outbound bandwidth from the leader becomes the bottleneck. And this is very simple. If you're trying to distribute a block of size m to n different participants, then in a typical traditional state machine replication system, that will all have to come from the leader. And this means that you need to send m times n bytes in traditional SMR. And now there's a new class of enhanced block propagation designs that are trying to get around this problem. And you see this in Narwhal Tusk was, I think, the most graceful first idea of how to handle this. Solana Turbine is another approach, and Monad has their Raptor Cast, which uses a tree in order to distribute the block, while also leveraging the entire validator set to distribute it. So these are all pursuing the same class optimizations, but enhanced block propagation allows you to handle blocks that are of a greater size. So with a 2 megabyte block, which you should be able to support on a reasonable size validator network without these techniques, that comes out to about 10K transactions per second, which is well above what we're operating at today on the Avalanche C-chain, and is also well above what I think every blockchain is, what every public and permissionless blockchain is operating at today. So although enhanced block propagation removes the bandwidth bottleneck around 10K TPS, and you can scale bandwidth horizontally with pilot fish-like designs where you add further workers in order to continue reproducing the bandwidth, this may not be, sorry, missed a slide. This is only going to be useful when you're trying to go from 10K transactions per second to a much, much higher number. So if you want to go from one to the next level, then enhanced block propagation is going to be very useful, but we have all of these other factors to consider as well. So if you have 2 megabytes of data and you want to go to, let's say, 20 megabytes, then this could be a very useful system. But if you have other factors that are going to be a bottleneck earlier than that, then it may not be relevant to you. And it may add additional complexity and additional trade-offs before you want to pursue it. Finally is state. This, I think, is the most complicated. State, the very simplest solution to this is to simply increase the memory requirements. There's also improved storage designs like Firewood, QMDB, and many more to come, as this is a very interesting space. There's sharding, proposer-builder separation, where you rely on very large machines to have full access to the state, and others are simply verifying it. And then there are designs like state expiry and state rent. So I think of this as the most multifaceted approach with many different solutions, and people are trying out a number of different ones. If you don't solve this problem, then it's not necessarily useful to solve the others. What you might notice, and what I think is very interesting and underappreciated, is that all of these have their own points on the trade-off curve, where you start to need to handle bandwidth around maybe 10,000 transactions per second. You start to need to handle state much earlier. If you're willing to throw a different amount of hardware at the problem, you might need to handle state earlier on in the process, or be willing to handle it later in the process. And this ends up being a very multifaceted optimization problem. So how can you cheat state? This is a very relevant topic because, as far as I can tell, Solana is one example, Aptos and Sui, and I think many others, actually fully turn off their disk when they're running their benchmarks. So if you look at Solana's own documentation on their benchmarks, they run at about, I think, 80K transactions per second, and then after that they turn off this actually writing that state to disk, and then say they can go much above this number. But this is not useful for a production system unless you solve that bottleneck, which they actually haven't. You never really see, another thing that I've seen a number of times is teams, I think the CBDC project from MIT actually did this, has come up with their own custom two-phase commit databases. And this is fine, but it's not anywhere close to a productionized database. So it's not really realistic, and there's no plans to bring it into production. So what you see oftentimes is that as people are building out their benchmarks, they run into a bottleneck at a different point, and they say, okay, the bottleneck is actually at the state level, and then they completely take that out of the process in order to see where they could get without it. This is very interesting from a computer science and optimization perspective, but for us practical system designers or product-led blockchain projects, we might not care about what's interesting if, how can we go past 10K, 80K, 100K, if all that we actually need is 5K in the most stable and predictable way possible. So where we are today in my opinion, is we have horizontally scalable designs, and the fact that this process is being explored is very, very good. I think that Sui, Aptos, Avalanche, and Sui, or Solana, and many others have pursued the design space to a point where we have some way to solve scalability by throwing more hardware at the problem and scaling up horizontally, which we didn't really have 5 to 10 years ago. So the fact that these optimizations are there and available is very, very good. But at the same time, we're often accepting optimizations that are tailored to the average case or are being tailored to these individual benchmarks that allow us to hit 1 million TPS or further in a case that we're never actually going to see in production. What I also find is that this is frequently increasing DOS concerns and the amount of complexity in the system. And this means that we're actually making system design decisions in order to cater to these benchmarks. So really in order to cater to that first joke slide of what benchmarks are for is tweets, VC pitch decks, etc. They're not necessarily built towards practical system design for people who are building, especially purpose-built chains or even general and permissionless chains that intend to operate in a Byzantine environment. So the next era, as I see it, and this is my big prediction, is that we're going to see diminishing marginal returns on performance. Blockchain has operated for a long time in a really sort of a beautiful twilight of everything is just an optimization, and there's been a massive amount of money that's been thrown at the problem. And today I think we really do have great optimizations and great designs that allow us to scale up horizontally along all of these dimensions. The last remaining one that I think really has a lot of interesting decisions to be made is state. But I think that we're very likely to see diminishing marginal returns on performance. If you look at applications today, very, very few of them actually demand greater throughput than what the best in class can offer today. So I think that what we'll see is actually shifting competition to distribution, extremely low barriers to entry with open source software by default, and then finally companies will be shifting to trying to capture value at the margins with sticky users and network effects. And so I think that what we'll see is these benchmarks, the focus is going to shift much more so towards how do we actually benchmark for an individual system, for our actual product and around users. And as more people come into the space, this will be much more important, thankfully, than all of the benchmarks that were catered towards Twitter, VC pitch decks, etc. So this is my bet for what the next era of blockchain performance looks like. Thank you.